Hello, students. Have you ever wondered why salt, sugar, and water look so different, yet all matter can be broken down into something more fundamental? Let's take a journey back in time to when philosophers asked, what is matter made of? Imagine ancient thinkers who believed that if you keep dividing matter, you'll eventually reach particles so tiny they can't be split further. They called these building blocks atoms. But science didn't stop there. As chemistry advanced, experiments showed that even the air you breathe and the food you eat are made of invisible, minuscule particles. This raised more questions. Why do elements like hydrogen and oxygen combine in precise ratios to make water? The answer comes from understanding how atoms join together, each acting like a tiny puzzle piece. And here's a core principle you see everywhere in chemistry: atoms are never created or destroyed in a chemical reaction. So, when you burn a log or rust an iron nail, the atoms themselves don't disappear, they just rearrange. This basic idea supports the law of conservation of mass, explaining why the total mass remains the same before and after any chemical change. Now, let's meet one of chemistry's pioneers, John Dalton. In the early 19th century, Dalton proposed something revolutionary. He said all matter is made up of tiny, indivisible particles called atoms. Atoms of the same element are identical, and atoms of different elements are different in every way, especially in their mass and chemical behavior. Dalton's theory didn't just sound logical, it explained real chemical observations. Why does water always have the same ratio of hydrogen to oxygen? Because Dalton showed that atoms combine in simple, whole number ratios. Think of H2O, where two hydrogen atoms join with one oxygen atom to make a water molecule. Dalton's ideas also gave us the law of definite proportions. Every chemical compound always contains exactly the same elements combined in the same fixed ratio by mass. But is the atom truly indivisible? Scientific discoveries soon revealed otherwise. Let's start with J. Thomson's famous cathode ray experiment. Imagine a glass tube with electric current passing through it. Thomson found that rays streaming from the cathode were made of negatively charged particles much smaller than any atom. He called them electrons. Next, scientists discovered the proton, a particle with a positive charge nearly 2000 times heavier than the electron. This explained why some parts of the atom attracted negatively charged electrons. But the story wasn't over. In 1932, James Chadwick found the neutron, a neutral particle with mass similar to the proton. This explained why atomic masses were higher than the sum of protons alone. So, atoms are made of three fundamental subatomic particles: electrons, protons, and neutrons. Let's visualize the atom as we know it today. According to Rutherford's nuclear model, the atom is mostly empty space. At its center is a tiny, dense nucleus containing protons and neutrons. Electrons whiz around the nucleus in defined orbits or shells. Think about this: almost all the atom's mass is packed into that tiny nucleus, while the electrons occupy a huge region of space compared to their size. Take hydrogen, the simplest atom. It has just one proton in the nucleus and one electron moving around it. The nucleus holds together because of the strong nuclear force, which keeps protons and neutrons tightly bound, even though protons naturally repel each other due to their positive charges. How do we distinguish one element from another? Every atom has an atomic number written as Z, which tells us how many protons are in its nucleus. This number is unique for each element. For example, hydrogen always has one proton, so its atomic number is 1. Oxygen has 8 protons, so its atomic number is 8. But what about atomic mass? That's the mass number, written as A, equal to the total number of protons plus neutrons in the nucleus. So, the formula is mass number A equals number of protons plus number of neutrons. Now, here's a fascinating twist: isotopes. These are atoms of the same element with the same number of protons but different numbers of neutrons. For hydrogen, there's prosium with 1 proton and 0 neutrons, deuterium with 1 proton and 1 neutron, and tritium with 1 proton and 2 neutrons. Isotopes play key roles in medicine, industry, and research. Now, let's look at how electrons are arranged in an atom. Electrons occupy shells or energy levels around the nucleus. Each shell can only hold a certain maximum number of electrons according to the formula maximum electrons in a shell equals to into n squared, where n is the shell number. For example, the first shell, called K, can hold 2 electrons. The second shell, L, can hold 8 electrons, and so on. Electrons always fill the lowest energy levels first. So, for sodium, which has atomic number 11, the electronic configuration is 2 electrons in the K shell, 8 in the L shell, and 1 in the M shell, spoken as 2, 8, 1. Let's put our understanding into practice with a worked example. Suppose we have an atom of chlorine with atomic number 17 and mass number 35. Step 1. The number of protons equals the atomic number, so that's 17 protons. Step 2. For a neutral atom, the number of electrons also equals the atomic number, so 17 electrons. Step 3. The number of neutrons equals mass number minus atomic number, that is 35 minus 17, which equals 18 neutrons. So, a chlorine atom contains 17 protons, 17 electrons, and 18 neutrons. Let's quickly recap what we've learned about atomic structure. The atomic model explains why elements behave the way they do, how they form compounds, and what makes each element unique. The discovery of electrons, protons, and neutrons gave us a deeper understanding of chemical reactions, the periodic table, and why matter is stable. Isotopes aren't just a classroom topic, they're used in hospitals for cancer treatment, in industry to check for leaks, and in science to trace environmental changes. By knowing how electrons are arranged and what atomic numbers mean, you'll be able to predict chemical reactions, understand electricity, and even explain why metals corrode or batteries work. I hope now you see how atomic theory connects the world around us, from the air in your lungs to the medicine you might need someday. See you in the next class, where we'll explore chemical bonding and how atoms come together to build everything you know.